Hello everyone. Welcome to my representation of towards large-scale incremental dense mapping using robot-centric implicit neural representation. Large-scale dense mapping is essential to various autonomous robotics tasks. The explicit dense mapping such as point cloud and voxel grids have been the mainstream for a long time. Its high efficiency makes it well applied in various robotics tasks, while their demanding memory consumption for fine details makes it hard to trade off between efficiency and accuracy for surface reconstruction, especially for large-scale scenes. Recent neural field has shown a promising future in various applications. The continuity of neural network gives the implicit dense mapping much more potential in reconstructing high granularity details. However, it still suffers from problems like low training efficiency and catastrophic forgetting problem. In this work, we aim to incrementally encode large-scale point cloud using both explicit and implicit representations to recover fine surface structure. We model a continuous implicit signed distance field with a combination of voxel grids and multi-layer perceptrons. Given arbitrary position falls in a voxel feature grids, a multi-resolution feature embedding will be obtained by trilinear interpolation with the involved neighbors. And this embedding will be fed to the MLP to get the signed distance. To model the space into a continuous field, we need to apply supervision points within our map. We assume that each point hits a specific surface. Near surface's space, we desire more sampling points to sculpture the fine detailed surface. The non-occupied space, so-called free space between the sensor and the hit points, we found it also essential to supervise them to a deterministic state to avoid floaters. Each sampling point will be assigned with a ray distance that formulates the distance from sampling point to the hit point along the ray. This ray distance will be treated as the ground truth for supervision. We proposed a robot-centric implicit mapping structure to conduct powerful bundle supervision and memory efficiency mapping, enabling large-scale incremental mapping and various applications. As shown in the left, it is obviously that the ray distance, shown in red line, is different from the truly signed distance that's shown in orange line, that indicates the distance of a point to its nearest surface. We use sigmoid function to map the signed distance value to the range between 0 and 1, and applies binary cross-entropy loss function to give higher weights to sampling points that near surfaces to avoid deviating signal contaminating the reconstructed signed distance field. Incremental neural mapping as a continual learning method suffers from catastrophic forgetting problems, where neural networks forget previously acquired knowledge during new learning phases. To address this problem, some researchers propose to use the keyframe idea from SLAM to pin the learnt feature, as shown in the middle figure's red cameras. While it requires delicate keyframe selection and maintenance strategies to get a good results, and other researchers regularize the update direction of learnable features to avoid easily deviating by new information. However, it sacrifices sort of training efficiency. Instead, we propose to adaptively store and sample historical point cloud to conduct bundle adjustment like supervision, so-called bundle supervision. We consider points as pins and the reconstruction surfaces as clothes. Each pin fixes the local reconstructed cloth from deviation. The proposed bundle supervision's advantages are threefold. First, we apply supervision evenly in the space that takes all view direction into consideration, have more accurate details than keyframe-based and regularization-based methods, though the accuracy is still behind traditional explicit-based methods like VDB fusion. The completeness and overall evaluation of our method is outperform others. Second, in incremental mapping that faces the catastrophic forgetting problem, bundle supervision pins the learned features more effectively and better mitigate the forgetting problem, have a better reconstruction results than others under a straight path in MESA-T datasets, and the ablation study also shows the effectiveness of our method. The zero-level set of the signed distance field defines the fitting surface. The input point's inference signed distance values naturally indicate the error of reconstruction. In dynamic scenes, the points on the moving objects will conflict with the free sampling supervisions lied between the static background and the sensor. According to this observation, we proposed an outlier removal strategy that periodically infers the signed distance values of historical points and drop points whose signed distance values are epsilon away from 0. After outlier removal, the previously learned outlier features will be unpinned and updated with the free sampling point supervision, as shown in the figures B, where the reconstructed surface on the walking person are cleaned by outlier removal. And we also found that this outlier removal strategy also helps to rebuild a tidier surface by removing noises introduced by sensor or inaccurate poses, as shown in figures A, and find the best fit surface in an iterative closest point way. Reconstructing a large-scale dense map necessitates demanding video RAM. The most straightforward idea is to divide the large scene into pieces of submaps and train them independently. However, non-overlapped submaps will introduce inconsistency into map, especially in submaps boundaries. To cope with these problems, we also divide the global map into non-overlapped submaps and propose a robot-centric mapping that trains the implicit model only on the local map whose origin slides with the robot's position without destroying or allocating memory. A simple index transformation one-to-one maps the local features to the global features without conflicts. To enable unbounded mapping, we craft a global map using a hash map. Specifically, with the movement, the slide-out features will be stored in global map, and slide-in features will be fetched from global map, and the submaps will be dynamically created and inserted to this hash map to enable unbounded mapping. An active frozen memory management strategy that only keep neighbor submaps to be kept in video memory, to help us to keep a constant low video memory consumption in mapping. The robot-centric mapping enables seamlessly and unbounded mapping. As we experimented in KITTI datasets, we show that we are capable to reconstruct a large-scale scenes using around 2 GB VRAM. The video memory usage remains constant at the expense of the system memory usage, and also with a decent running efficiency and reconstruction quality. In summary, this paper introduced an efficient, scalable, robot-centric implicit mapping using range sensors. Key to our system is the subtle leverage of the robot-centric local map, proposing bundle supervision, which enhances both training efficiency, mapping quality, and addressing the catastrophic forgetting phenomenon encountered in continual learning. A flexible global map structure tailored for robot-centric implicit mapping to preserve a reusable map and reconstruct an unbounded large scene with a constant low video RAM. Our codes is also open source for communities. And that's all. Thank you for your listening.